Another quick example I want to talk about is I'm going to find all functions whose derivatives are equal to themselves. This is an example that we talked about previously. And we're going to separate variables. This one's actually easier than the one that we did before. And so we're going to have y prime, we're going to write as dy dx. And we're going to separate variables. So we end up with 1 over y dy equals dx. And then we integrate both sides. Okay, so we get the y's on one side, the x's on the other, and then we integrate both sides. And when we do that, we're going to end up with, let's see, 1 over y, the integral of that's going to be the natural log of the absolute value of y. Then we'll have x plus c. Okay, and so that tells us that the absolute value of y, if we exponentiate both sides, will be e to the x plus c, or e to the x times e to the c if we separate those out. Or remember, c just stands for generic constant. E to the c is another constant. So this tells us that the absolute value of y is actually c times e to the x. Now, one last thing that we can do, exponentials are always positive. And so we can actually drop the absolute value if we want at any point here. Let's just erase it here. Okay, so we're allowed to drop the absolute value because exponentials are always positive. And then this e to the c we rewrote as c. So if you don't like that, if you want to call this c1 and this c2, that's totally fine. But they both just stand for generic constants. So I'm just going to call them both c, with the understanding that they don't stand for any specific number. That means that every function whose derivative is equal to itself looks like this for some constant c. Okay, it's always a constant times an exponential, even the zero function. Remember, of course, if you have the zero function, that's a function whose derivative is equal to itself. That would be when c is 0. Okay, so every possible function whose derivative is equal to itself looks like this. Okay, so there's another separable equation.